So this is part 2. This is going through the second half of the June 2018 Chemistry paper 1. So this is for triple scientists. You can find the paper on the website shown, and you can have a go and mark along as you see fit. So we're given some data about temperature changes in displacement reactions with copper sulfate solution and different metals. And you're asked to plot this on a bar chart. Now helpfully they told you they want a bar chart, but they might not have. They might have just asked you to plot that data, and you need to recognise that the independent variable, the metal, is categoric. And so for categoric data we will draw a bar chart, okay? If it was continuous data for both axes, then it would be a line graph. So here it is plotted here. We have labelled the metals, we have picked an appropriate scale, so my data is not all squashed up in one corner. My scale is consistent, all those things will get you marks. So 5.2, the student concluded the reaction between the metals and copper sulfate solution are endothermic. Give one reason why it's incorrect. So endothermic reactions take energy in, endothermic enter, as we sometimes use. So that would mean we would observe a decrease in temperature, but we observed that the temperature increased. An increase in temperature shows that it's an exothermic reaction. So you are told the temperature change depends on the reactivity of the metal. The student's results are used to place copper, iron, magnesium and zinc in order of their reactivity. Describe a method to find the position of the unknown metal in this reactivity series. Your method should give valid results. So there are lots of different methods you can use. The mark scheme lists 4. I'm just going to go through one of them, but look on the mark scheme on the AQA website to see the others. So you're going to add the unknown metal to the copper sulfate solution, and you're going to measure the temperature change. Now measuring that temperature change is important there. If you just say measure the temperature, you'll probably lose that mark because we need to know the start temperature and the end temperature. That's covered by saying measure the temperature change. But you can alternatively say measure the start temperature, measure the highest temperature. Later on, you can then place the temperatures in order of temperature change to get the reactivity. Now we want our experiment to give valid results, so we need to make sure we're using the same mass of metal each time and the same volume of copper sulfate solution. They only want you to mention one of them to get that mark for control variables, but we want to make sure it's a comparable test. Like I said, look on the full mark scheme for other methods you could use. So you are asked to draw a fully labelled reaction profile for the reaction between zinc and copper sulfate solution. So we know already this is an exothermic reaction, so that's the shaped curve we're looking for. Now with exothermic reaction, the energy is released to the surroundings. So if we think about the store of chemical energy, the reactant will have more energy than the products. So we expect to see reactants at a high level to the products. They expect you to label up the activation energy, and you can use the capital E lowercase a for this if you wish to, and they expect to have the energy change or delta H labelled on there too to get the other marks. So, a student investigating electrolysis of different substances. Why does this setup not work? So they've labelled the zinc chloride as being solid. Ionic substances, when solid, cannot conduct electricity. It has to be molten so the ions are free to move around and carry the charge. So we're then asked, why can graphite conduct electricity? And explains in terms of structure and bonding. So they want you to recognise that each carbon is covalently bonded to 3 other carbons. So each carbon has one delocalised electron, which is able to carry the charge through the structure. I've split these up into 3 bullet points to show you where you are getting the marks on this question. But any questions about electricity, you're looking at the movement of charge through the structure. How is that done? Is it being carried by electrons? Is it being carried by ions in the case of ionic substances? So we're showing a different setup here of the electrolysis of sodium chloride solution, and we can see they're collecting gases there. The students made an error in selecting the apparatus for this investigation. How should the apparatus change? So we want to go through, we've got graphite electrode, that's fine, we've got power supply, we've got positive and negative electrode there, it's on DC current, that's all good. So we need to look at the test tube. So we are trying in this investigation to measure the volume of gas. And if we use test tubes, there's no scale on the test tube. So what we want to use instead is something like a measuring cylinder. We can put it in upside down, filled with some electrolyte, and that will collect with gas. Alternatively, you could use an inverted burette, or we could use gas syringes. Both would be sensible. So we have another student's data here, and we're asked to describe the trend, and we're told this is 3 marks. So when describing what is going on the graph, you ideally want to describe the trend, what happens when one thing increases, what happens to the other. If you can back that up with data, that is also really useful. And you also want to point out if there is any changes in rate of reaction. So there are multiple things you could get marks for on this paper, on this graph, and different ways you could phrase it. But they're looking for things like the volume of hydrogen is directly proportional. See that nice straight line there? And you could work out the rate, and that would get you a mark, and we do that by using the gradient. We could say up to 8 minutes, the chlorine is collecting at an increasing rate. After 8 minutes, it is directly proportional, it is the same rate as the hydrogen. Didn't have to say all of them to get the marks, any 3 of them would be good. So, number of moles of each gas produced is the same. No, a gas escapes from the apparatus, so just one reason for the difference in volume, and they showed us there was a difference in volume in the diagram. So why would there be a difference? So we know that gases occupy the same volume, the same number of moles at the same temperature and pressure, so that's not going to be the difference. What is the difference is that chlorine will dissolve or react in the water, and that will get you the credit. So we're asked to calculate the amount in moles of chlorine collected after 20 minutes. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeter cubes. Give your answer in standard form. They also hint that we need to use a graph. So they've mentioned 24 decimeter cubes. That tells me I want to use this equation, moles equals volume divided by 24. So I need to get my volume from the graph, and if I go back and do that, I get a value of 6.6 centimeters cubed. Now in all these mole calculations, our units need to be in decimeter cubed. So we convert to decimeter cubed and we get a value of 0.0066 decimeter cubed. So I can now plug these numbers into the mole equal volume divided by 24, and I get an answer of 0.000275 moles. But the question has asked me to give my answer in standard form. So that's what I do, and convert it to 2.75 times 10 to the minus 4 moles. You're getting the marks here for, first mark is for getting 0.0066 decimeter cubed, so read the number correctly and then converted it. Second number is for using the values correctly in the equation. Third mark is for giving your answer in standard form. So this question is about group 7. Chlorine is more reactive than iodine. Name the products formed when chlorine solution reacts with potassium iodide solution. So this is going to be a displacement reaction, and the products formed are potassium chloride and iodine. So we're then asked to explain why chlorine is more reactive than iodine, and I've put up the electron structures of 3 of the group 7 elements, and we can see as we go down the group we have more shells, and we can also see being group 7 they all have 7 electrons in their outer shell, and they are kind of aiming to get an extra electron in that shell, so they're trying to attract an electron when they are reacting. So what can we say about chlorine? Chlorine outer shell is closer to the nucleus, and the nucleus being positively charged has a greater than attraction on those outer shell electrons, and so that makes it much easier for it to gain an electron. So we're told that bromine reacts with methane in sunlight, and we have a figure showing the display formulae for the reaction of bromine with methane. And we're given the bond energy and the overall energy change in the reaction in the table. So asked to work out what X is using the diagram figure 9 and the table. So we need to remember that delta H, or the total energy change, is the sum of the energy required to break the bonds minus the sum of the energy required to form the bonds. So with these questions, they're quite common. Pitfalls to look out for is they sometimes give you the display formula but not necessarily the correct number, so they're not in a balanced equation form. So do make sure you're multiplying by the right number of bonds. But in this one they've been quite nice, they've given us the straight diagram. So question 8, we're looking at titanium being a type transition metal, and we're looking at extraction. So we've got links to both C1 and C4 in this question. So titanium is extracted from titanium dioxide in 2 stages. Stage 1, titanium oxide plus carbon plus chlorine forms titanium chloride and carbon monoxide. In stage 2, they take that titanium chloride and react it with sodium to form titanium and sodium chloride. So just one hazard associated in stage 1. So we need to look at the reactants and products in stage 1 and see if any of them are hazardous. And there are 2 which jump out at me which you could mention. So we have Cl2, chlorine, that is a toxic gas, and that is obviously very harmful. But we're also producing a toxic gas in carbon monoxide, which is very poisonous, and we've mentioned a few times in the chemistry course. For 8.2, water must be kept away from reaction stage 2. Give one reason why it'd be hazardous if water came into contact with sodium. So I think the probably most common answer we'd see from students is that sodium reacts violently, and that would be credit worthy. But we can use other words to describe that. We could say it's an explosive reaction, it's a very exothermic reaction. We could also mention that when it reacts, it produces sodium hydroxide, which is highly corrosive. We can also say that hydrogen gas is produced, and that is explosive and flammable. So you've got a few directions to go in. They would not give you credit for saying it's a vigorous reaction, and they would not give you credit for saying it is very reactive. That won't cut it. For 8.3, they suggest why the reaction stage 2 is carried out in an atmosphere of argon and not in air. So argon is a noble gas, so it has a full outer shell, so it's unreactive, or we could say inert. So it's not going to react with sodium. But if we had used air, there's oxygen and water vapour in the air, and both of those potentially would have reacted with the sodium, and that would not have been desirable. So titanium chloride is a liquid at room temperature. Explain why we would not expect titanium chloride to be a liquid at room temperature. So we need to think about what type of bonding is going on here. We've got a metal and a non-metal. So titanium chloride is ionically bonded. Now, ionic substances normally form huge lattice structures, think sodium chloride, and so we would expect them to be solid because there are lots and lots of electrostatic forces to overcome. So they will give you credit for identifying titanium chloride as ionic bonded, for saying that they are usually solid at room temperature or they have high melting points, and saying why ionic substances have these high melting points. And that's because of the many strong electrostatic forces of attractions. You can't say there are many bonds to overcome because it's not bonds where breaking here is electrostatic forces of attraction that we are overcoming. So, in stage 2, sodium displaces titanium from titanium chloride. Sodium atoms are oxidised to sodium ions in this reaction. So, why is this an oxidation reaction? So, oxidation is the loss of electrons or gain of oxygen, and in this reaction the sodium is losing electrons. The only thing you need to actually say to get this mark is that sodium loses electrons. Job done. So you want to complete the half equation for the oxidation reaction for 8.6. So sodium is in group 1, that means it's got 1 electron in its outer shell which it is going to lose. So that will form a sodium plus ion, as there's now more protons than electrons, so it's a positive charge, and then we have our 1 electron there. What we need to do first is look at what is the sum of the energy of the bonds broken, and then look at the sum of the energy of the bond made. So I can see, if I'm looking at the bond broken, is basically all our reactants. We presume every bond in the reactant side is broken. So that means we've got 4 carbon-hydrogen bonds, and those straight lines on those diagrams represent a bond. So we do 4 times 412. We then have 1 bromine-bromine bond, so that's 193, and we add that together to get a total amount of energy for the bond broken of 1841 kilojoules per mole. Then what we presume is that every single bond is made. So we have 3 carbon-hydrogen bonds, 1 hydrogen-bromine bond, and then we have our mystery bond, the 1 carbon-bromine bond. So we hear the total amount of energy required to make the bonds is 1602 plus our mystery number x, which is what we're trying to work out. So if we plug in the information we know into the equation shown, we know that minus 51, that value in the table, equals 1841 minus our 1602 plus x. So I rearrange that equation to find x, and I get a value of x of 290 kilojoules per mole. So here we've got a calculation looking at stage 2 part. So we have 40 kilograms of titanium chloride being added to 20 kilograms of sodium. Note the masses are in kilograms. If we're doing calculations, we want them to be in grams, so we're going to need to convert them. The equation for the reaction is shown, and we've got some relative atomic masses. Explain why titanium chloride is a limiting reactant. You must show your workings. So if you don't show your workings, you're not going to get credit. You can't just say without any workings titanium chloride is just in excess. So the way to approach this is to think about how many moles do we have of titanium chloride, how many moles of sodium will react with that number of moles, then find out how many moles of sodium there actually are, and then compare those values. You could work out how many moles we have of sodium versus then how many titanium chloride react with, and do it that way around. Either is perfectly valid. So the moles of titanium chloride equals the mass divided by the MR. So 40,000 grams divided by 190. So I remember to convert my mass into grams there. And that tells me that there are 211 moles of titanium chloride which are going to react. Now, we now need to say how many moles of sodium will that react with. This is where we look at our equation and we look at the ratio of moles of titanium chloride to sodium. And if we look at the equation, this is a 1:4 ratio. So, if we've got 211 moles of titanium chloride, it is going to react with 844 moles of sodium. So now we need to see, well, how many moles of sodium did we put into that reaction? So we had 20 kilograms, that's 20,000 grams. We divide it by the AR of 23, and that gives us 870 moles. So if we compare those numbers, for the amount of titanium we had, it only needs to react with 844. So we've got more sodium than we need, and that shows that the sodium is in excess and that the titanium chloride is the limited reactant. So, the stage 2 reaction, the percentage yield was 92.3%. The theoretical maximum mass of titanium produced in this batch was 13.5 kilograms. So you need to calculate the actual mass of titanium produced. So, we have the formula percentage yield equals actual yield divided by theoretical yield times 100. So, what you got over what you should have got times 100. So we know the percentage yield, we know the theoretical yield, so we need to rearrange for actual yield. So we rearrange, so we get percentage yield divided by 100 times theoretical yield, and that gives us a value of 92.3 divided by 100 times that by 13.5, and you should get the answer of 12.5 kilograms. So this question is about acid alkali. That means it's relating to the C4 module chemical changes. Dilute hydrochloric acid is a strong acid. Explain why an acid can be described as both strong and dilute. So, whether an acid is strong or weak refers to its ability to dissociate or to ionize in solution. And whether an acid is dilute or concentrated refers to how much of the acid is present in a given volume of liquid. So, hydrochloric acid is a strong acid. It fully dissociates, so it completely splits into H plus and Cl minus. Another example of a strong acid would be sulfuric acid, where you get H plus acids in solution, H plus ions in solution, and you get SO4 2 minus ions in solution. Then we have ethanoic acid, otherwise known as vinegar, which is a weak acid. It only partially dissociates. You do get the H plus ion being liberated, but you can see there's a lot of hydrogen still trapped in that structure. So for the marks for this question, you need to say that strong acids completely dissociate, but being dilute means there's only a small amount of acid in a given volume, or you can say per unit volume. This question tells you that a 1 times 10 to the minus 3 moles per decimeter cube solution of HCl has a pH of 3. What is the pH of a 1 times 10 to the minus 5 moles per decimeter cube solution of hydrochloric acid? So you need to be aware that pH equals the minus log base 10 of the hydrogen ions. This can be arranged, so if you know the hydrogen ion concentration equals 10 to the power of the minus pH. So in this case, 10 to the power minus 5, the pH is 5. So a titration question here, and there are lots of parts to this, but there are lots of marks to be gained, even if you're intimidated by these questions right at the end of the paper. So a student titrated 25 centimetres cubed of dilute sulfuric acid with a 0.105 moles per decimeter cube sodium hydroxide solution, and we can see their results there. The equation for reaction is 2 moles of sodium hydroxide react with 1 mole of sulfuric acid to form 1 mole of sodium sulfate and 2 moles of water. The question wants you to calculate the concentration of sulfuric acid in moles per decimeter cube. Use only the student's concordant results. Concordant results are those within 0.1 centimeter cube of each other. There's some helpful clues there. So we're trying to get concentration. So that the concentration equals moles divided by volume. So we need to know the moles of the sulfuric acid. We don't have that yet, but we can work it out. We want to use concordant results. So we're going to be looking at that table and go, right, which results are close together, which ones am I going to ignore, and we're going to use an average. So you want to strategize with these types of questions. So if you want to have a go at it, this is how you break it down. First, calculate what titra will you use, and then calculate an average of them. This is worth 2 marks, which is quite a big chunk of this. Then you want to work out, using that average titra, how many moles of sodium hydroxide have you used. You can use that information with the equation to say how many moles of sulfuric acid there were, and then you can work out the concentration. So if you want to pause and have a go, now would be a good point. So let's go through these steps. What titra will you use? You're going to use 3, 4 and 5, and that gives you an average of 22.13 centimetres cubed. So how many moles of sodium hydroxide? So moles equals volume times concentration. I'm going to plug the numbers in. So note that I've had to divide the volume by 1,000. That's because the volume has to be in decimeter cube, not centimeter cube. So how many moles of sulfuric acid do I have? Now we've got to look at the equation. We can see that the sodium hydroxide to sulfuric acid has a 2-to-1 ratio. So I'm going to use every mole of sodium hydroxide, I'm going to use half that number of the sulfuric acid. So I'm going to times my number by 0.5 or divide by 2, same thing, and get moles of sulfuric acid to be in 0.001162. What is the concentration then? Concentration is moles divided by volume. So plug the numbers in, again converting my volumes into decimeter cubed, and I get an answer of 0.0464 moles per decimeter cubed. They're looking for a minimum of 2 significant figures. Just be aware of that. So we're asked to explain why students should use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide solution. So pipettes are used to measure a fixed volume accurately, but burette measures a variable volume. That's all you need to know. Good thing to have on a flashcard. 9.5. Then asked to calculate the mass of sodium hydroxide in 30 centimetres cubed of a 0.105 mole decimetre cube solution. And we were given the relative formula mass of 40, which was nice of them. So, moles equals volume times concentration. So, 30 divided by 1000, making sure my units of volume are in decimetre cubed, times by 0.105, gives me moles of sodium hydroxide of 0.00315. I have the moles, I can now use that to work out the mass, because mass equals moles times MR. So 0.00315 times 40 gives me an answer of 0.126 grams.